Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. Okay, today we will continue with the next chapter which is chapter number 2, Arithmetic Logic Unit for the course of BEE 3233 Electronic System Design. So basically, an overview of where this Arithmetic Logic Unit circuit is. Now, in the previous class, we had seen the first part, which is the implementation technologies, in which we had looked into a couple of ways of implementing this. We had started off with PLD, Programmable Logic Devices, in which we had looked into two methods. The first one is Programmable Array Logic, and the other one is Programmable Logic Array. Secondly, we move into FPGA, in which the concept that is being utilized by FPGA is by using lookup table. Okay, we are going to continue with the next chapter, which is to discuss about arithmetic logic circuit that consists of three main elements. Okay, the first one would be adder, multiplier, and arithmetic logic unit itself. Okay, we will begin with adder, in which I will introduce you to four concepts of adders. The first one is the most simple version of adder, which is known as half adder, followed by full adder, and later ripple carry adder, also move on until carry look ahead adder. Okay. After this, we will continue with finite state machine, before I will introduce you to Verilog and also test bench, in which we will look into how to design these digital design concepts in FPGA and how to implement it on FPGA. Okay, then only we will do lab number 1, which is addressing the adder needs, and also lab number 2, which is addressing the ALU, before we move on into project, which is the finite state machine. Okay, let's have a look on binary adding process. So this is an example of adding two numbers. The uppermost is equivalent to 21, whereas the lower numbers is equivalent to 7. So by adding these two together, you should get 28. So in binary, 21 is being represented by a 5-bit binary numbers, which is 10101, followed by 700111. Okay, just a reminder, this is equivalent to the power of 0, to the power of 1, 2, 3, 4. Alright, so let's have a look on this first addition. So we have here 1 plus 1, which is equivalent to 2. So to do this, 2 is equivalent to 1, 0. So how do we note this? Is by having 0 here and 1 being carried out to the second phase. This item is known as carry out, whereby once it comes to this part, it is known as carry in. The second addition is 0 plus 1, which is equivalent to 1. But remember, it has the carry in of 1 that is being carried from the previous addition. So it is equivalent to 1 plus 1, which is also equivalent to 2. So in this case, we should write here as 0 and 1 being carried out to the next addition. This is followed through until the last segment. Note that there is a number here, which is the last segment, which is in this case, it is 0. So this is preserved as 0. Sometimes you will see that this will result in 1. That is the process of binary addition. Okay. So the truth table that is related for this addition is by having, say for example, this is X and this is Y. So when 0 plus 0, it should equivalent to 0. So in this case, the sum is 0, whereas the carry out is also 0. 0 plus 1 is equivalent to 1, and there is no carry out. Similar to 1 plus 0, which is equivalent to 1 with 0 carry out. However, look, when 1 plus 1, which is equivalent to 2. So in this case, 0 is being preserved, whereas the 1 is being carried out. This addition is known as half adder. Let's have a look on the full cycle. Note that there are differences between these two. The first one here consists of only x and y, which is the outgone and added, whereas for the full adder, which is the bottom truth table, consists of x, y, and also the element of carry in, which is being carried through from the carry out of the previous addition. Okay, let's have a look on this addition. When x is 0, y is 0, and c in is 0. 0 plus 0 plus 0, which is equivalent to 0. No carry out. Say for example c in is 1, so 0 plus 0 plus 1 is equivalent to 1, which denotes sum as 1 and 0 for carry out. This continues until, look at this example, 1 plus 1, which is equivalent to 2. So in this case, sum is equivalent to 0, whereas the carry out bit is equivalent to 1. And this is followed through until all the sequence is being covered. When we have 3 variables, meaning that there should be 8 possibilities. So in this case, this is 1 plus 1 plus 1, which is equivalent to 3. And in this case, sum is equivalent to 1, whereas cout is also equivalent to 1. This is known as full adder. Full adder is a complete cycle of an adder, whereas half adder is the partial addition of an adder. Alright, now let's move on into the digital construction of both half adder and full adder. This is half adder. While this is full adder. Okay. From this truth table, let's derive a Karnaugh map. Now, why do we derive a Karnaugh map? It is because to get the simplified equation. Once we get a simplified equation, we can get the simplified version of the circuit. Okay. So take for this example, this is the Karnaugh map for the sum. So here is equivalent to x bar y bar, which is equivalent to 0. X bar y bar, that is equivalent to 0. The second item, x bar y, which is equivalent to y. X bar y, which is equivalent to y. This is followed through until the end. So from this Karnaugh map representation, we can see that there are 2 loops that can be derived. The first one is this part and the second one is this part. So this is equivalent to x y bar, which is this portion, whereas this is equivalent to x bar y, which is this portion. Now, looking into the behavior of logic circuit, this combination x y bar or x bar y is equivalent to x or y. Let's move on into cout. Similarly, to transfer from truth table to Karnaugh map is like what we had done before. So in this case, for cout, x bar y bar is equivalent to 0. The only part in which it is equivalent to 1 is when x is 1 and y is 1, which is being represented by x and y here. The loops that can be derived is this part, which is equivalent to x, y. So in this case, it is equivalent to x and y. So by deriving this equation, we can translate this into a half adder. Exclusive OR for sum and AND for cout. Similar process is being done for a full adder. First, we transfer from the truth table for sum into the Karnaugh map. Note that there are 4 simplified versions of loops here, and it is being represented by this equation. X bar y bar c in followed by X bar Y, C in bar, and through till the end. Once we have derived this, we will continue with C out. Note that the elements here are the input, whereas the elements here are the output. The numbers of Karnaugh map that should be derived should be equivalent to the numbers of output. From the equation that is being derived, we can transfer this into logic circuits, as shown on the left-hand side. Now, the process that had been shown earlier is known as a ripple carry process. Ripple means wave, which means that the first bit has to complete its cycle, then only move on into the second bit addition, followed by the third bit, fourth bit, and so on. This means that if we are required to do a 32-bit addition, meaning that we require at least 31 cycles to do so. Okay. So this is an example of the implementation using full adder with carry-in properties. The first bit addition, followed by the second bit addition, third bit addition, fourth bit addition, and fifth bit addition. So this is known as 5-bit ripple carry adder, as the carry out is being rippled as the carry in to the next addition process. So this can be simplified in this term. In previous example, we are denoting this as C in or C out and continue through. Note that there is a sample here that is being mentioned here as +1. Note that there is an addition that is being mentioned here as I +1, which means that the next bit for this C out. And this is for the current sum properties. So this addition can be simplified into these two equations as a general representation for the ripple carry adder. So if we were to expand this into the following, we can see that the properties here, G, generation bit, is equivalent to X, I, and YI. Whereas propagation bit is equivalent to X, I, X or Y. Okay, so looking here, we can see that these properties is similar to these properties, whereas this is also similar with the XI, X or Y properties. Now, the carry out properties of the second stage is equivalent to generated bit plus propagation bit Ci. So where does this come from? You can have a look of this generation bit that is equivalent to Xi, Yi as being defined here. Hence, we can simplify the next C out is equivalent to generated bit plus propagation of the current bit multiplied by current bit. So for the first addition cycle, we can do the prediction by having this item. So Ci is the carry in for the first bit, for the second cycle, for the third cycle, and for the fourth cycle. Okay. So the properties of Ci here, which is equivalent to G, generation bit at 0th level, and propagation bit at 0th level, can be simplified into this equation. Likewise, C2 here can be simplified into this version, as well as C3 here can be simplified at this version. Now, note that the difference between the first step that is being shown earlier, ripple carry adder, to the one that I've shown here is that the fourth bit of the carry in can be predicted at a second stage of addition. by predicting what the C stage 1, stage 2, stage 3 is adding or is being derived from. So we can transfer this into circuit. Okay. Looking into the previous example, if you look here, the second addition can only happen when first is being done. Okay. The third addition can happen only when the first and the second cycle is being done, followed through till the end. However, by having this prediction of G, generated bit, and also P, propagated bit, we can expedite the process by estimating the output or the input that is being generated. Look at this stage in which this carry-in is being predicted not within this bound but also earlier, at an earlier stage, in which carry-in for the first cycle is being predicted by the C0, P0 and G0 at the first addition. G0, P0 and C0. So does the second stage of addition, which is being predicted here at the first instance by knowing the properties of C0, P0 and P1, as well as G0, P1 and also G1. Also for the fourth bit addition, which is being predicted by the third generated items followed by propagated item of the third layer. For the third layer, similar process is being done. By having these additional circuits, the prediction can be done within the first and the second cycle, because it is being predicted not while waiting the addition process is being done. These are the pink element, which is equivalent to A, I exclusive or BI, current state, which is being fed into the third, the first, the second and the fourth addition cycle. This is an example of the generated bit of GI, which is being fed accordingly as shown here. So, the first concept that was shown earlier is known as ripple carry adder, in which the second stage can only be added once the first bit has finished, followed by the second stage, third stage, fourth stage and continue on. Whereas for carry look ahead adder, this can be done in parallel. Hence, it requires only at least 3 cycles to complete fourth level of addition. Whereas for the ripple carry adder, the adder concept that is being shown in the beginning would require 8 cycles in order to complete 4-bit addition. So this is termed as ripple carry look ahead adder. Now, the second item that we are going to look is multiplier. So before we look into the digital adding or the digital circuit that is related to this multiplier, let's have a look on the multiplication process that is involved. Say for example, we have two numbers, 2-bit numbers, B0 and B1, as well as 2-bit numbers of A0 and A1. For multiplication, 0 multiplied by 0 is equivalent to 0. 0 multiplied by 1, 0. 1 multiplied by 0, 0. And 1 multiplied by 1 is 1. Now, looking at this profile, this is similar to A and B properties. So, by having this concept, we can further expand this 2-bit multiplication. So, the first item A0, B0, followed by A0, B1. This item is when A0 multiplied by B1. Then we move on into the second multiplication process, which is A1 multiplied by 0 and A1 multiplied by 1, which is equivalent as shown. Once this is being done, the addition process should take place. If we look here, this element is being fed directly as P, product of 0, element number 0. These two addition will result in product element of number 1, number 2, and number 3. So once we had determined this, we can translate it to a digital circuit. Once we had done this process, we can translate it into a digital circuit, as shown here. Note that these are the elements associated with the process that has been explained earlier. And the addition process between this first and second layer is being represented by this full adder. Sorry, by this half adder. There is no carry-in properties here. Okay. So now we move on into 4-bit multiplication, which is more or less equivalent to the 2-bit multiplication with the expansion of addition process. As shown earlier, the first string will start off by multiplying B0, A0, B0, A1, B0, A2, and continue until B0, A3, followed by the B1 process, B2 process, and also B3 process. So to transfer this into digital circuits, this is equivalent to an AND gate, in which both the product of A0, B0 is equivalent to A0 and B0. This arrangement is being purposely done so that the addition process can be done intuitively. If we look here, this element is being directly moved as the sum properties of bit 0. The addition of these two processes is equivalent to S1, followed through by the third stage, fourth stage, fifth stage, and so on. Now, there are instances in which you can use half adder. Remember, half adder properties only has the properties of X, Y, carry out, and sum. Whereas for a full adder circuit, you will have X, Y, and also carry in as the input. For the carry out, there will be carry out properties as well as the sum properties. There are 5 input-output elements, 3 inputs, 2 outputs, as compared to half adder, which consists of 2 input elements and 2 output elements. So as being suggested here, the first tier of addition of the second stage can be done by using half adder. For the second stage, you will require one set of full adder and also a set of half adder. Look at the fourth addition, in which it requires at least 2 sets of full adder to complete the addition, as well as a unit of half adder, as this involves 4 additions of numbers. Then 3 addition of numbers requires the same 2 full adders and also 1 half adder, followed by 2 half full adder, and the final bit, which is equivalent to 1 full adder. As the name suggests, arithmetic logic unit is a unit that could do 2 main things. The first one is to complete the arithmetic process, and the second one is to complete the logic process. Now, arithmetic consists of processes such as addition, multiplication, comparison, subtraction, and so on. Whereas logic unit consists of logic element consists of process such as AND, OR, exclusive OR, and so on. So arithmetic logic unit ALU is one of the core items in CPU, central processing unit. Now here there is a suggestion of video that you could watch to understand better on arithmetic logic unit and CPU function in a computer. So for arithmetic logic unit, for this course, you need to master at least 2 items on how to implement the arithmetic portion and also the logic portion. This is an example of an ALU, in which it has 2 properties, A, B, and also Cin as well as S for the select. And it has two output properties, which are F and Cout. Note that multiplexer is always synonym with arithmetic logic unit. The build-up of a multiplexer is input and also output, as well as the element of select, as shown here. S here denotes select. Now, the properties of multiplexer can come into the form of 2 to the power of n for the input. N is the number of select. So, for example, in this case, when there are 4 inputs, meaning that the select should be 2. 2 to the power of 2 is equivalent to 4. This is the input properties, whereas this is 2 to the power of n. N here denotes the select, the numbers of select bit. Okay, so having said here, you will find in the market there will be 2 to the power of 1, which is equivalent 2 to 1, 2 to the power of 2, which is equivalent to 4 to 1 multiplexer, 2 to the power of 3, which is equivalent to 8 to 1 multiplexer. The variation of the sizes. Okay, the working mechanism of a multiplexer is similar to switch, which means that if there is a 4 to 1 multiplexer, the input will take turns to feed in the output. Hence, we'll switch between the first, second, third, fourth, and so on in order to feed in the input to the output. Here is an example of a build-up of a multiplexer. In this case, it is known as 4 to 1 multiplexer, whereby there are 4 input and 1 output. 4 is equivalent to 2 to the power of 2, which means that this multiplexer should have 2 selects. So in this case, it is select 0 and select 1, representing bit 0 and bit 1. So the internal structure of this multiplexer is as shown here on the left hand side. So the internal structure of a multiplexer is as shown here, in which A, B, C, and D are the inputs and X are the selects properties. In this case, there are 2 selects element and also an output. So that's all for chapter number 2. To recap, you should be able to explain the operating mechanism of adder. There are 4 variations of adder that is being discussed: half adder, full adder, ripple carry adder, and carry look ahead adder. Then we had looked into multiplication process of 2-bit numbers as well as 4-bit numbers. Here, you should be able to do the multiplication process as well as to derive the digital circuit that is related to this multiplier. And the third item is the ALU, as shown in the last segment, which stands for Arithmetic Logic Unit. This unit should be capable of doing 2 things: to do the mathematical operation, which is known as arithmetic operation, and also to do the logic, which is equivalent to the 7 logic properties. So that's all for chapter number 2. We'll see you later in chapter number 3. Assalamualaikum.